and welcome to module 5, network design and planning. So in this module we are going to study about the network design principles, and there are three principles which we are going to focus on: scalability, redundancy and performance. So let's understand what is network design principle. Network design principle acts as an architectural blueprint for building reliable, efficient, and adaptable IT infrastructure. And the three pillars are scalability, redundancy, and performance. So basically, these three are like the parameters which we need to ensure that they are taken care when you are designing the network. So let's look at the first one, scalability. Scalability is network's ability to grow and accommodate increasing demand as more users, devices, or data traffic without experiencing drop in performance or requiring a complete redesign. Now, the last 2 points are very important. So even if there is an increase in number of users or increase in the number of devices that have been added, or if the traffic increases, the performance of the network should not drop, or you should not require a change in the design of the network or network architecture. Now, how do we achieve scalability? So there are three methods: hierarchical design, modularity, and standardization. So these three methods would help us to achieve scalability. The first is hierarchical design. Break the network into logical tiers. Now this is pretty self-explanatory. Rather than connecting everything to one single switch or few set of switches, where this few set of switches or the single switch would become a single point of a failure, and obviously you will not be able to increase the number of devices that are connected, as an example, or the traffic will not be able to be managed by that switch. So what do we do is we break this into layers or tiers. In the next slide we will be studying about three-tier Cisco three-tier architecture in detail, so right now I'll skip that. Modularity: design the network in independent self-contained modules that can be upgraded or expanded independently. For example, let's say IT Lab 6. Okay, we have a separate switch where all the machines from the IT Lab 6 get connected, or IT Lab 2, we have a separate switch where all the machines from the IT Lab 2 gets connected. Now, if I want to make any change in that lab, the changes in that lab will be contained within that lab itself, right? It will not affect the entire network. Now that's the beauty of being modularity. Okay, whenever you have to upgrade or you want to expand the network, it becomes easier. So if I want to increase the number of machines and my switch is insufficient, I may use one more switch and connect them as a stackable switch. So that's where the modularity helps me. Standardization: using standardized protocols and hardware types to ensure new equipment integrates easily. So standardized protocols examples are OSPF or BGP, which all the vendors, you purchase a router or switch of any vendor, and this kind of a routing protocols which are standardized protocols will be supported. So what happens is, if I want to expand a network and I have brought a new router, it will also be compatible with the existing ones. So the scalability becomes easier. Hierarchical design, which is also called as Cisco three-tier architecture or three-tier architecture. What this basically is when you're connecting the networks, we will connect it in the layers, like the access layer, distribution layer, and a core layer. So the end user devices like your laptops, your computers, your peripheral devices like printers or Xerox machines, network based Xerox machines I meant to say, they can be connected on an access layer. So the user devices directly connects to the access layer. So this you can imagine as, this is your IT Lab 6 switch and all the machines are connected here. This is your IT Lab 2 switch and all the machines are connected. This is your IT Lab 3 switch and all the machines are connected. Okay, so that's where I am having an access layer network devices. Now what happens is I need to aggregate this traffic and send it to the server. Okay, so let's say my server room is on the first floor and these three labs are on the third floor. So it might quite be possible that I'm having one switch where the entire floor's data is aggregated. So my IT lab 6 is also connected to this third floor switch, IT lab 3 switch is connected to the third floor switch, and IT lab 2 switch is connected to this third floor switch. Now this third floor switch is connected to a server room switch, and to this core switch there are different servers connected. Okay, now this is a very rudimentary kind of an explanation for a three-tier architecture, but as we go into the details, as we see some of the designs, you would be able to appreciate why this three-layer architecture is so important. One reason is of course the scalability, because if I want to make any changes in the access layer, it remains confined only to this layer. If I want to make a change in the department level switch, so let's say if there is a problem with the second floor switch, then only second floor gets affected. But at the same time, there is some concept of redundancy which we will see later on, which will help even if there is a failure in one floor switch, still you can access through another route. Okay, so that's the beauty of this Cisco three-tier architecture. Now going to the next thing, that is redundancy. So scalability is one factor which is important. Redundancy is the next factor which is important. Redundancy is the intentional duplication of critical network components. Now mark here critical network components. So the network components which are something which, if they fail, can create a problem, may create a situation where entire network goes down, or those are connected to a very important servers, then or those are connected to a very important departments, so then it becomes my critical network component. As well as and communication links to eliminate single point of failure. So what is the goal? The goal is developing architecture which is fault tolerant. So even if something goes wrong, still I have an alternate way of doing the things. Now how do we achieve this method of redundancy? So there are three ways: multiple data paths, hardware duplication, and failover protocols. So what do we mean by multiple data path? Running multiple physical cables between the critical switches or routers, so that if one link fails, the traffic flows through other. It's pretty self-explanatory. So if there are alternate path, if one link fails, the traffic moves through the other link. Hardware duplication, installing backup devices like dual core switches or secondary firewall configured in active standby or active modes. So when we talk about hardware duplication, it means basically you are having a standby device which is ready, or a backup device which is ready. So if the primary device fails, if the main device fails, I have the secondary device on which the entire load of the network can be transferred. Like I have a switch, say in one of the lab, if it is a very critical lab, I may have two switches. Okay, one is a backup switch and one is a main switch. So the main switch may be active and the backup switch may be just sitting on a standby. So if something goes wrong, I can just pull the cables and put into another switch, and the network is up within say 5 minutes or 10 minutes of time. Okay, there are different ways of keeping the hardware device active. So I'll not go into active standby or an active mode right now, but that is something which we'll be doing a bit later when we start with the designs. Failover protocols. Utilizing protocols like spanning tree protocol to prevent network loops while keeping backup paths on standby, or first hop redundancy protocol to prevent backup default, to provide backup default gateway for the end user devices. What basically means here is there are certain protocols which are available when let's say for example on a router I can configure an event based triggers where if the primary link fails, automatically within 30 seconds a backup link comes up. So the traffic which was coming on primary link will get diverted onto the backup link. So there are protocols which support this kind of mechanism. Those are called as a failover protocols. So the failover protocols are used for automated transition to the secondary systems. So the transition can happen in two ways. One is you will require an administrator to configure. Once he or she detects the failure, then you manually configure it. The other is you can have a protocol which detects and automatically transfers. The third is the performance. The performance dictates how efficiently and quickly the network delivers data from source to the destination. So the whole idea here is you have a good network, fine, but there's no point in having that network if the delivery of the data is not guaranteed, or if the delivery of the data is extensively delayed, right? So there are certain metrics which are used to understand the performance of the network. So there are four metrics: bandwidth, throughput, latency, and jitter. Okay, so based on those four metrics, how does the network perform on these four metrics? We evaluate the performance of the network. Now there are three methods which are used to achieve performance. The first is quality of service, the second is load balancing, and third is traffic shaping. Now what do we mean by quality of service? Prioritizing critical or delay sensitive traffics like VoIP, that is voice over IP, or video conferencing over less important traffics like a background file download during times of congestion. So let us say if there is a video conference going on, then obviously the video conferencing, the discussion that is happening or the frames of those videos happen to be time sensitive, right? So this is something which needs to get a priority over a file transfer that is happening. The file transfer, even if the chunks comes delayed, there's not much of an impact, because at the end of the day you're going to just assemble that all the chunks and read it as a whole file, right? You're not waiting for the file to immediately get downloaded. But in VoIP or video conferencing, if there is a delay, then that delay can be felt by the user. So therefore there is a sense of a quality of service, and creating a priority channels for those different types of a traffic is something which can help you to configure to achieve performance. So there are ways by which the networking devices can be configured for the quality of services. The second is the load balancing. When you have everything flowing through one single router or one single switch, obviously that single switch or a single device would get overwhelmed, and that is where the traffic bottleneck happens. So why don't we create multiple paths for simultaneous communication? And this is what is exactly meant by load balancing. So distributing the entire network traffic which is flowing through multiple devices so that a single device does not become a bottleneck. The third is traffic shaping, regulating the flow of the data into the network to ensure a smooth, predictable stream rather than overwhelming burst of traffic. We had already seen one of the example of a protocol which does traffic shaping, that is a leaky bucket algorithm. The whole idea is that you don't want a burst to enter into the network because that can cause congestion and therefore degrade the performance. So there are different algorithms and protocols which does traffic shaping and ensure there is a predictable stream which is entering into the network rather than the burst of data. So that's it in this video. Thank you very much.